Hi, everybody. Um, Thank you for having me here on such a short notice. I like if you need me again, please let me know. um, so before we start going really deep into what I'm gonna talk about and about magnetism and about all those things, I suggest I try to put myself within the scales that were introduced this morning. So Miguel, for instance, said in the beginning that there is this scale, right? So there are two axes, and then here comes the ab initio, here comes the atomistic simulation, here comes something hybrid coarse grained, and there what people do. So this is me. I do that. That is what people do. I'm that people. So I'm doing that coarse grading that is exactly falling in that scale. So it would lack probably in comparison to the previous two talks, would lack quite some chemical detail. But what I will try to convince you though, is that it's not so bad. So those people also have the right to exist somehow. So I mean, we justify our existence in the way I will tell you. And the story will be the following. So I would walk you through the points. So I would tell you about what magnetic soft matter is and why we think it is interesting. And there, I would also try to convince you what exactly is needed to be done for it to be even more useful than it is now. Then I would introduce my methods. Then we would focus on two types of systems that are called multicore magnetic nanoparticles and magnetic nanogels. And then finally, conclusions and outlook. So, what is magnetic soft matter? Imagine that, there is an old joke dating back to 2011 to a liquid matter conference in Vienna, and that was done by Dan Frankel, whose name probably all of you know. And the joke was, what is soft matter? If you go to the airport, you can see this plastic bag filled with gels, etc., that you cannot bring on board unless it is in a given volume. So this all is soft matter. So that's exactly what you need, like, to minimize in volume in order to carry on board. So these are liquids, gels, pharmaceuticals, foods, dyes. I mean, whatever. It's really it's a lot of things. And now imagine that you want to have a biologically compatible control over soft matter. We heard a lot about pH, about extreme values of pH, about ionic transport this morning, but you don't want to have ionic transport or highly highly active electrophoresis in your blood vessels. That is very suboptimal. And what you need, if you want to control or drag something through the blood vessels, you need a control engine that like manages to distantly, so from distance, actually transport those things. And magnetic is perfect to this extent. Why? Because it doesn't interfere with living tissues at all. So if you bind needed chemicals to a magnetic particle that is small enough, and we come to this in a moment, then hypothetically, with an applied magnetic field, you can transport this medicine to the target and then apply it there. How big should the particle be? So in order to penetrate the cell, it should overcome the brain barrier. So the brain-blood barrier for the cell is critical. So the particle cannot be larger than a micron, or better, does not exceed something like 200 nanometers, 500 nanometers in diameter. So that would be a good size. In general, people did not think about it in that terms 60 years ago. The first object that was synthesized as magnetic soft matter, and I'm trying to use the pointer, there was a ferrofluid. What is a ferrofluid? Ferrofluid was synthesized by Ron Rosenzweig and his colleagues as an aircraft fuel. It was a very ambitious idea and project of NASA that never worked, but the impact remained. And the story is that these are magnetic nanoparticles, approximately between 10 and 50 nanometers in diameter, suspended in a liquid carrier. And then if you put such a magnetic fluid on a substrate in a petri dish, and you put magnet from below, what you have magnetic field lines going through the fluid, magnetic nanoparticles trying to follow the field lines, the surface tension of the fluid pulling them back, and that's what you see that got the name. No, sorry. That's what got the name of Rosenzweig instability, that hedgehog. That was 1964. Since then, synthesis went up, and so did the applications of those magnetic nanoparticles suspended in liquid carriers. And coming back to what I started with, the idea of biomedical applications is probably nowadays the most important ones in the whole story of magnetic soft matter. So you can do particles like ellipsoids, platelets. You can take magnetic nanoparticles and glue them rigidly together to build multicore particles, or so-called nanoflowers. You can connect them into polymer-like structures where each monomer is a magnetic nanoparticle. And all this basically is done in order to optimize the heating properties. So because when you bring a magnetic nanoparticle to a certain place with an AC field, you can rotate this magnetic nanoparticle and it will locally hit the target. This is called magnetic hypothermia. It's not necessarily to treat cancer, as you might think, or that people usually claim it is for. Actually, any heating or any mixing would work with this purpose, so with this kind of mechanism. Another thing is the transport process. So if I can transport these pharmaceuticals. And another advantage of this kind of heating or transport is that it is extremely localized. So unlike chemotherapy for cancer, for instance, that affects also healthy cells, local heating affects only tumor cells because the particles are held basically inside the tumor. So now, what kind of particles should that be in order to optimize the heating? And that would be the question that we would try to answer at the end of this presentation. So how do I design a particle that being transported to a target actually heats properly? And in order to do this, I will use that molecular dynamics simulations. And let me tell you a little more about the method. So basically, I would use only two basic potentials. So it's a very simplified, very coarse-grained model. So my particles would have excluded volume. That will be modeled by Lennard-Jones potential that is truncated and shifted. That is called WCA, Weeks-Chandler-Anderson potential. And the second one would be dipole-dipole potential. That is the interaction of two perfectly magnetized spheres. In this situation, my system can be characterized by two important parameters that I want you to remember. One is so-called lambda parameter, and it characterizes the dipole interaction. So the interaction of two core-line dipoles, m, whose value is m, to thermal energy and divided by size. So it's a dimensional ratio of dipole interaction to thermal energy. And the second parameter is the concentration. As long as we are now on a nanometer scale, we have to take into account that the entropy and the interactions are competing both when structure of these systems is formed and when they respond to applied stimuli. So that's why we will operate this parameter and this parameter. I will show you a little later that this is not really all that simple. So, but what if I want now, instead of a spherical particle, to have a particle that has an exotic shape, say an ellipsoid or a platelet? In this situation, technically you have two options. So first, you can model a shape as a closed potential if this shape is geometrically describable, like a superquadratic, for instance, like a superball. That you can do. Then you can plug in something that looks like Weeks-Chandler-Anderson potential, but contains some more elaborated distance expressions. So in principle, you can do that, but there are very few shapes that can be described that way. So one of the basically simplest and cheapest approaches is to build your shape out of spherical particles. And then you rigidly bind them together so that they stay in this shape throughout your molecular dynamics simulations. Alternative method would be to have a geometrical shape which is not a closed form of a function, and then on each step to solve a system of algebraic equations whether or not you have an overlap. And this is too costly, way too costly to do that. So in this sense, having those particles bound together is an advantage in terms of calculational speed, but it also has extra advantage. So for instance, if you don't want to have only a point dipole that is in the center of this particle, but you have some distributed set of dipoles within these particles, you can assign to each of these raspberry bead, they're called raspberry representations for obvious reasons. Each raspberry bead can have basically a dipole moment. So this is what we do. And in this situation, what you need to remember is basically that lambda really shows that head-to-tail orientation of dipoles is good, that anti-parallel orientation is still not bad, but then parallel and most like nose-to-nose configurations are really bad. And please, we are not talking about sauna and being wrapped and not being wrapped here. So it's just exclusively talking about the orientation of dipoles, okay? So I mean, I missed the starting point of that discussion, but I'm afraid of causing some reactions there. So what does the Zeeman interaction do to the dipole moment? It tries, as an applied field, I lost, yes, it tries to align the dipole moment along the field direction. So these are the basic interactions. Okay, let's go to a more interesting stuff. So what do we know about magnetic nanoparticles in liquid carriers? We know that due to these dipole-dipole interactions, even in the absence of an external field, if magnetic interactions are stronger than thermal interactions, those particles will form chains that clearly are head to tail, and they're lovely. But even better, if lambda is higher, is even stronger magnetic interaction in the system, they will form rings. So chains and rings. Right. So do we want to have chains and rings in blood vessels? Well, it depends on their size. In principle, it's not such a bad thing, particularly considering that chain is very responsive to an applied field. But what about rings? Rings are not. Rings are closed form. They have a zero magnetic moment. So rings are bad. Okay, now, can we quantify that? So let's assume a very simple model. You have a magnetic particle, it has a magnetic moment, and if an AC field applied, then the magnetic moment due to Zeeman energy follows the applied field, but it is so rigidly bound to the particle body that the whole particle rotates. It's a point dipole approximation. So what happens in this condition? It is the whole particle rotation. So we have a full particle rotation, it causes friction, that is how the heat is generated. Now, what do we know about this? We can measure in a system the magnetic moment autocorrelation function. It will look like this, and it is characterized as an autocorrelation function of the magnetization of a particle or of the whole system with respect to its zero moment orientation. And this very C of t, once it is Fourier transformed, will give you the so-called dynamic susceptibility. That is very similar if you're acquainted with broadband dielectric spectroscopy. Is exactly the same expression as there. So it's exactly the same approach. And it is, of course, just a linear response approximation for that. So what is important there? The important part is this guy. So the imaginary part of the dynamic susceptibility is what is responsible for the power loss. So the dissipation, this is the dissipation, is what shows you a resonance frequency on which the applied field should be applied in order to reach the maximum heating. So the position of the maximum of the imaginary part of the susceptibility is what you are interested in overall. So this is what we will be looking at. Right. So we have, in a simple case, so if particles do not interact, we have a classical debye spectra, a monodisperse spectra, a polydisperse spectra. This is a real part of the susceptibility. This is the imaginary part. And you have only one maximum. This maximum is responsible for this. So it is exactly located on the frequency that is inverse Brownian relaxation time. That is the rotation, and the Brownian relaxation time depends on the viscosity and the volume of the particle. Right. Now, if instead you start adding some interactions, the debye spectra, the classical debye spectra, changes, and changes pretty much. So you can see that the position and the height of the imaginary susceptibility changes. Now let's try to understand how exactly it changes. We did quite some simulations to that extent, and we discovered that if you increase the interactions and chains and rings are formed, either branch structures at high density, what happens is that a single peak, a single debye peak of the imaginary susceptibility actually splits in two. There are two peaks, so it means that there are two eigenfrequencies in the system. Which kind of frequencies are that? So one is the rotation of the whole cluster. So the whole cluster rotates, and this comes lower than a single particle Brownian rotation. However, within this cluster, the particle vibrates. It leaves, and this goes higher than the Brownian relaxation. So it's a higher frequency process. So by interactions, solely interactions of a point dipole particles, you can split already the spectra of the dynamic susceptibility into two maxima of the imaginary part. What does it tell us? It actually tells us that you can both hit on this frequency and on this frequency. Why frequency is important and not only the amplitude of the field? There is a physiological limit of a patient which frequency and which strength of the field you can apply. It's called so-called Brezovich criteria. I mean, it is arguable, but is one of the references that is currently on the market. And this is the product of frequency times the amplitude. If the particles are very strongly interacting and they are forming rings, in principle, the frequency they will be susceptible to is quite low. But the problem is that they are already clustered in rings, as we talked previously, and this makes them magnetically very reluctant to the applied field. So they wouldn't. So you need a strong field. Instead, those local frequencies, the whole cluster will not feel that kind of perturbation. But this oscillation will change. But then, again, you need a very high frequency. So point dipole is in general a very simplified approximation. Why? Because we know that magnetic particle is not only what that people on that side of the spectra do, but also what chemists do, and it has a crystalline structure. And it means that there are directions within a crystalline lattice that are easier to magnetize than another due to exchange interaction, due to spin-spin interaction. So what happens there? It means that the particle, each magnetic particle, has two mechanisms to relax. One is the whole particle rotates, as we said, Brownian mechanism, but another option is when the magnetization actually jumps inside the body of the particle. And this is so-called Néel relaxation. This Néel relaxation is much faster and it only matters if the particle is small enough and the crystalline anisotropy is weak enough. So basically, if you even have a single particle that allows you both relaxation mechanisms, you immediately get a split of the spectra, because there is a frequency on which the Néel relaxation is agitated, and there is a frequency at which still the Brownian relaxation is agitated. So we're having already two. Now, but it has exactly the same problem. Néel relaxing particles are super small. Brownian relaxing particles are large and highly interacting. And the idea came, first of all, we need in our simulations to get rid of this single dipole approximation and do something more. The problem is, look at the time scales. They're several of orders of magnitude apart. So what kind of time step would you need to integrate your equation of motions to reproduce both timescales? It's a challenge. It's a technical challenge. And the second thing is that maybe we need to play on the anisotropy, on the internal anisotropy, and go somewhere in between and find the right frequency, or at least the right spectrum. So we proposed three different mechanisms how to take into account the internal anisotropy. One is the simplistic one. This is an ideal superparamagnetic particle. So it's infinitely polarizable. So the field applied, and it has a non-linear reaction to the field, but the point dipole always will point in the direction of an applied field unless there are dipolar fields in the system and interactions. The other model is based on basically solid-state physics, and this is related to Stoner-Wolfert approach. And this relies on two minima states. So you have an easy axis of magnetization. So there is a crystalline lattice favorable orientation of the magnetization, and it can only switch within this orientation depending on the energy barrier. However, for nanoparticles, you need to add thermal perturbations, so you add on top of it a probability of a switch that is not related to an applied magnetic field. So you combine technically molecular dynamics with a Monte Carlo step. So you do equation of motion, you calculate the field acting on each particle, you calculate the probability of a switch, you either switch or you don't switch. This is good model, very fast working model for very anisotropic particles. When the particles are not that anisotropic, you don't expect two-state model to work properly. So instead of being either here or here, the magnetization can actually have a precession around the easy axis. And this is a frequency, this is its own frequency of oscillations that has to be taken into account. And then it can also point outwards of the easy axis. And for that, it took us several years of work, but we combined the solution of Brownian dynamics with a solution of Landau-Lifshitz-Hilbert equation. So it's a so-called egg model. So you model the dynamics of the magnetic moment that is connected by a spring to the whole particle. And that's why it looks like an egg, like a yolk, right? And the yellow part is rotating with friction, with viscous friction inside. So this is a moment, and the whole particle is an egg. And in this situation, what you have really an accurate solution of Landau-Lifshitz-Hilbert equation. So you get very accurate magnetization dynamics. Of course, you need to go to the time step that resolves Landau-Lifshitz-Hilbert time step, right? Or you update, so you do a combined step, so not exactly the same step for molecular dynamics and the solution of Landau-Lifshitz-Gilbert. So what do we get? First idea that was probably proposed something 15 years ago. Let's glue the particles together. Let's build so-called multicore particles. What will we get in this situation? We will get cores that are rigidly bound in a polymer shell, or it can be just like they're chemically glued together. They have no Brownian degrees of freedom per se. The whole colloid has, though, a rotational degree of freedom. There are a lot of discussions going on whether or not you need or not need the exchange interaction between the cores. So far, people think that it matters, but not that much. We will not consider that. So this is a so-called nanoflowers. So these are our colleagues from Sorbonne. This is from the group of Ladislav Ekos from Timisoara. Right. So we modeled them, as I said, as a raspberry. We already had an approach, and each core now has its own anisotropy. So the model is like that. So you have a multicore particle. Each core has an anisotropy axis, and what I do, I let those particles relax, and I change the lambda, the interaction between the cores, and the anisotropy that is characterized by a parameter kappa. Kappa is the energy, the anisotropy energy that is proportional to the volume divided by the thermal energy. So when you have small anisotropy and small interaction, what basically you have a red spectra of the angles between the easy axis and the orientation of the dipole. No interactions, no anisotropy manage to create a preferred orientation of the magnetization inside the multicore. If the interactions are very weak, but the anisotropy is very high, all dipoles are oriented along the anisotropy axis. There is a very interesting intermediate state when the interaction is strong and the anisotropy is strong, and then you start seeing the competition. If instead the interaction is very strong and no matter how anisotropic is, the anisotropy cannot anymore hold any ordering of the dipole moments. How is it reflected in the susceptibility? It turns out that the higher the susceptibility of the so the higher the interaction between the cores in the multicore is, the lower is the susceptibility. So the interactions block the cores, and when you apply the field, there is no way you can go out. And if you look at this part, you will see that the same effect has the anisotropy if the interactions are weak. But if the interactions are strong, the anisotropy leads to a slight increase in susceptibility. So because it blocks the interactions, so it keeps the dipoles inside relatively disordered. So what happens in the spectrum? There are a lot of curves. I don't want you to look at all of them. Well, of course, I want you to look at all of them, but I just want you to understand several ones. So if the interaction is small and the anisotropy is small, you get a perfect Debye spectra. One peak, nothing matters. The peak will be at the eigen frequency of a single core. If you have very weak interactions and very strong anisotropy, it's basically a Debye spectra with a peak that is the rotation of the whole multicore particle, because everything else is blocked by the anisotropy inside the cores. Right. And what happens here is that you still see a small appearance of this. And this is the second peak. This is the high frequency peak that is related to a single core. So, and you can see, if you look at this position, it's at 1, and at this position here, and now you compare it to this position and this position. So this is very strongly interacting cores. What happened to this peak position? It shifted towards higher frequencies. This peak is related to the rotation of the whole multicore as total, doesn't change the position. And it's clear because the size of the multicore and the viscosity of the fluid is not affected by the internal structure. So take-home message from this spectra is, by tuning both interactions and anisotropy, you can very strongly change, look here, it's the most interesting case again, intermediate interactions, intermediate anisotropy. You can have a very strong shift of this eigenfrequency of the core. So you get actually the least distance between those. You can even get rid fully of the Brownian relaxation in this situation because it would be too slow. So in comparison to that. So if you calculate the specific loss power, you will see that for low interactions, you get very nice, very clear, like saturation. So you basically have only those frequencies to maximize. But as soon as you start getting a plateau, that suggests you a new frequency. So, and you can see that you start having those oscillations in this regime. Again, if you go to too strong interactions, you're again in a two-plateau system. But this is the point where one can try to tune it more accurately. Right, this was a rigid assembly. Let me drive you rapidly through a non-rigid assembly. This is a magnetic nanogel. It's a polymer matrix in which the magnetic particles are embedded and can move. So unlike the cores of a multicore, these guys are mobile. They can't freely rotate because they're penalized by the elastic matrix. I promised to dance, so and basically what happens here is that you add on top of a rotational Brownian frequency, you have also an elastic frequency of the matrix that can be manipulated in order to access some different peaks. So what do we get here? Let's stick to point dipoles. We just have this frequency, their own frequency, and again, the gel still has a frequency of its own rotation as a colloidal particle, even though it's of course very different from a hard ball. So soft colloid and hard colloid in a liquid, they of course have different Brownian relaxation mechanisms, right? So they do it differently because in one case, the solvent is not penetrating into a colloid, and in this case, the solvent can go through. It's basically a hydrogel with magnetic nanoparticles in it. How do we model it? So this is our spherical horse in vacuum. This is how we imagine polymers. So they're beads connected by springs, and we use that to create a nanogel. So we put our polymers into a spherical confinement. We let them relax. It's similar to what is called emulsion synthesis. So when polymers are injected in droplets and then cross-linkers are injected in those droplets, and then the cross-linking is occurring within the droplet. And that creates you pretty monodisperse nanogels. And the magnetic particles are chemically bound to polymers. We do it even simpler, which is take a couple of beads and announce them magnetic. So for us, that is what we need. And we also play with the morphology. So we can do Gaussian, inverse Gaussian. So it's a core, basically core is, so it's a vesicle. So it has an empty core and a shell, and dense core and a corona, or a uniform distribution of cross-linkers. And we calculate first the normal susceptibility. And what we see here, we see a very clear tendency. So the less cross-linkers you have, for weak magnetic particles, you basically see very slow, very low effect of interactions here. These strongly cross-linked systems induce proximity of magnetic particles that are in the gel. So the more it is cross-linked, the more closer they tend to be. if the magnetism instead is strong, in a weakly cross-linked gel, the magnetic particles have a lot of degrees of freedom and they can cluster as they want and close into rings. And so the static susceptibility for highly interacting particles with a growing quantity of magnetic particles goes down, as for non-embedded into a gel matrix particles. But if the cross-linking is strong enough, then the elastic matrix stop particles from aggregating and the susceptibility doesn't really go down. What happens on the dynamic spectrum? This is a very difficult, so this is really a very computationally costly approach. So we had to have an adaptive step to calculate those magnetization autocorrelation functions, because the difference in the time scales of a single particle relaxation magnetic particle and the whole gel is really different. The red curve is the experimental result for nanogels with the same magnetic content and uniform distribution of crosslinkers. So you can see two things. You can see that the eigenfrequency of rotation is very similar. It's a very similar effect, like if particles are clustered. So the frequency is very high. So it's a very, very fast vibration inside the gel. And the oscillation of the gel are very slow. So you again have a very clear split that mildly can be actually tuned by the crosslinker distribution, but clearly only very mildly. So I'm wrapping up. What did we see? I remind you, right? Where did we start? We started that we want these magnetic particles of some kind to actually hit. For that, we need to have a full control over not only the position, but also the height of the imaginary part of the maximum of the imaginary part of the dynamic susceptibility. And because that is what gives you the heat production. Debye says you have Brownian relaxation, you have one peak heat on that. If we assume a Debye model for a real magnetic fluid or for a real system that will be used in mice or even in patients, that would be utterly wrong. That is clear. Even if you assume a superposition of Debyes, this is not the case. So what we saw instead was this. So first, you have an interplay between this Néel and Brownian mechanism that can be further enhanced by introducing accurate description of anisotropy of the cores, so playing between the size of the time scale of Néel and Brownian relaxations. You can also play by actually changing the concentration of crosslinkers or magnetic content inside a soft colloid. In principle, that is less controllable. You can control the aggregation. And all this never gives you a single Debye peak. None of them are Debye. So take-home messages are this. So even weak interactions need to be taken into account when describing dynamic spectrum. For multicore particles, you really need to fine-tune the interplay between the interaction of the cores and the anisotropy. And this is material problem. So you need to have a certain number of cores, a certain size of the multicore particle, and a certain really composition that allows such a unique combination. And it's not a trivial task. And in nanogels, they are good for transport because they're porous and they can contain a lot of substance, but they are almost uncontrollable in this sense. So it's very difficult to tune their dynamic response. However, so the main conclusion is if you wanna like find or tune this resonance frequency like of the or eigenfrequency of the system, still these three parameters can be very valuable and very useful. That probably is something that has not been considered yet in a basically ensemble of properties. With that, I want to thank people involved in this work, people from the University of Vienna, from the Euro Federal University, and Field Camp from the University of Edinburgh, and you for your attention.
Thank you very much. It was a very nice talk. And okay, we have our first question.
Hi, thank you very much for your talk. I really like gels and your gels, magnetic gels. What I have an understanding is, okay, you have a, say, chain A and chain B, so they are entangled just with in terms of magnetic force, right?
Not quite.
Not quite.
So basically, what happens is that you chemically cross-link them necessarily. So, I mean, you can have physical gels that are due to magnetic interactions, but they're very unstable. So any flow will just disentangle those kind of constructions.
So it's a kind of collaboration with magnetic field and covalent.
Yes. So the cross-linkers are covalent bonds for sure. That is necessary. And then what you need, I mean, that's what they do for hydrogels. So I'm talking about those PNIPAM things. And what they do, they also chemically bind magnetic particles. So they're not trapped in the pockets, because that is a very important part. If they're not chemically bound to an elastic matrix, their rotation is not at all constrained by being in a polymer matrix. It's just the viscosity of a solvent where they're rotating. So there is no impact of the elasticity of the polymer.
Okay, that makes sense. Thank you.
Any more question? Alexei?
Just you were speaking about the usage of rotation for heating. Will it disturb the system actually? Because, for instance, if you implanted all these particles somewhere, right, and then you utilize absorption within the particle due to internal rotation of the spin, that's one thing. You kind of disturb surrounding less. Whereas if the particle as a whole, they start rotating, it may be some consequences for your tissues, no?
In general, what people want, they want what is the right emphasis of apoptosis of those cells. So if they're mechanically disrupted, even better. So that is not that bad. That is good. And if people are not using it within a tumor, but using for, say, industrial heating and melting of a polymer by those particles, which is now a very hot topic for some reason. I don't know why they came to it now again, but it became again a very subject to discuss. And there you particularly need to disrupt. So there actually mechanical disruption of the polymer bonds is exactly what you need for melting those systems, to enhance melting. So if you need to locally instead measure the viscosity of a cell, because some cancerous cells have a different viscosity, also it's an indication for this liquid-liquid phase separation in cells that is also particularly hot nowadays. But there you can measure local viscosity in different parts of the cell with a magnetic particle. There you don't need a disruption, but there you also necessarily don't need an internal relaxation, because otherwise the viscosity measurements would not be exact.
And at the beginning you were speaking about the delivery of the particles with magnetic field. Is it realistic, or people intend to inject, these particles, particularly in a tumor? Or how is going to happen?
So,
they use some kind of surfactant specific or antigens that will bring those particles to the tumor through the blood?
So thanks to Paul, we had a recent update from Pankhurst in Eger on that. And injection is working already on patients. So that is already clinically approved. So that part of hypothermia is working. What is not clinically approved is a clot disruption for Alzheimer by transporting the magnetic clusters and really mechanically disrupting those bilayers so that those stuck layers. Now, magnetic gels are used for experimental patients and experimental treatments for transport. That works. And also porous particles filled with magnetic nanoparticles are used to in blood vessels to be transported in gradient fields. So that is done. It's not medically approved, and it will probably take another 15 years, if ever. But it is realistic. It is working. So you just need really very, very, very subtle interplay, and you need liters of those systems if you want them to work in actual applications. So you need a method. So first you need a recipe, but then you need a chemical method.
The injections work, as you said.
Injections work. All surface tumors, brain tumors, breast tumors.
What is the success rate?
Very high. So it's a very high ratio. I mean, at least what Pankhurst showed, right? I mean, what people actually owing the machines say, they say that the enhancement of treatment is very high. So also they make millions on that. I would be very surprised if they say, oh, we inject these magnetic particles and nothing damned work. Right? It would be very weird. So I don't think they would say that. But at least literature says there is a huge enhancement.
Mm-hmm. Okay. Thank you.
Hi, first of all, it's a very interesting talk. Like, I really enjoyed it. Thank you. Coming from a synthetic perspective, I knew that the nano grains are particularly important in these types of systems. And I've always wondered what's the temperature effect in affecting these systems, because some magnetized systems, they can have like hysteresis loss in the magnetization curve. Like, what's your take on this?
Oh, that's a beautiful question. Yes. So you need to find magnetic material whose Curie temperature is far away from any heating range you're working at. If you get a transition from a ferromagnet, say, or so from a like anti-ferromagnet, anti-ferrimagnet, anything with a remanence, to something that becomes super paramagnetic, so you destroy the order, the spin ordering, you're screwed. Because there is nothing, and you can't take out those particles anymore, because, I mean, unless the destruction of spin order is reversible for some reason, like, so it's a very smart material, but usually once it's like destroyed, it's destroyed, and then you can take the particles out. So what people do, they still use biodegradable iron oxides so that they can be like changed into ferritin and whatever, so that the body actually, so the patient doesn't die from cirrhosis. I mean, not from cancer, but from cirrhosis is still not the optimal thing, right? If all this metal gets to the liver, you don't want that. But I mean, there probably, if it gets demagnetized, it's even better. But still, yeah. So it's a very accurate choice of Curie temperatures, and you can quite tune them. So in this sense, you can tune particularly in multicores. That is a very easy thing, because if you allow exchange interaction between the grains, you can really very accurately tune that.
Thank you so much.
Thank you. So, any additional question? No, in that case, let's thank Sofia for this beautiful lecture.